Good evening, everyone, and I'm Elena. I'm one of the TAs in the Data Analytics program, and the purpose of tonight's meeting is to go over running the linear regression, logistic regression, and naive Bayes method in RStudio. So here is a brief agenda, and I realize we have a lot to cover tonight, so we're going to do the linear regression. We're going to learn how to build the model, how to do the residual plots, and how to do the minimal adequate model. And here in the logistic regression method, I have a bonus for you. So for people who attend this meeting or for people who watch the recording, I'm going to show how to do the RAG curve. And we also do naive Bayes. All right, so let me go ahead and get started. I'm going to share my screen. Share my screen. So here is an RStudio, and we're going to get started with the regression, linear regression, and I'm going to be looking at the data set called forest fires. So let me go ahead and import the data set. Of course, I can use I can do it programmatically just by running the command, but I'm going to show you how to use this interface. To import interface, import dataset, and I'm going to select from local file. Now, what I did was I have a folder, and I called it dataset, and in that folder, I have a dataset called forest fires. Right, here it is. So I'm going to select it, and that just gives you an idea what my data looks like. So this is the actual data in the CSV file, and here I see the preview, right? So what I'm going to do is, this looks correct, right? This is what I want. I want the first row to be variable names, right? And I'm going to go ahead and hit import now. There we go. So that's how my data looks like. And in this case, this data set, I can tell you it doesn't have any missing values. So we don't need to worry about that part. And most of the variables are numeric, but we do have some factor variables. So what I recommend you guys to do is, you might want to run the summary command, right? You might want to see forest, right? I'm going to show you what I mean here. You want to look at your categorical variables, and you want to make sure that you don't have a value that only one or two instances have, right? You don't want to have a value that only one instance has. And I'm going to explain it to you why. And the reason is because the way we run the linear regression model is we need to divide our data into two sets. The first set is going to be 70% of the data, and we're going to use it to build the model. And that part of data is called the training set. The remaining 30% is going to be the test set, right? Now, let's continue. So what you need to do, guys, you need to set the seed, right? You set the seed on, and what it does is it sets a random value, okay? Because what I want to happen is that I want my result to be reproducible, right? Since I want my result to be reproducible, I have to set seed. Now, what I'm going to do is I'm going to divide my data into the test set and the training set, okay? And I need to divide my data into the training set and the test set. So what I'm doing here, this is going to be training, right? And this is going to be set. This is going to be test, okay? So now let me run this command. Run. Okay? Now what I'll need to do is, I'm going to need to build my model, right? I'm going to need to build the model. And it's going to take two input parameters. The first input parameter is going to be the formula. And the second input parameter is going to be the data, right? So, the way it works is that the formula, I have to put the dependent variable name, or the variable that I'm predicting, and it has to put the tilde, right? I put tilde, and here I have to put the list of my independent variables. Okay, so wildcard dot means that I want to have my area dependent variable, and I want to use the rest of the variables in the data set as independent variables. So that is basically the wildcard, right? So here, this is the data, right? And I'm going to use my train data, right? 70% of the data set is used for training. And this is what I'm going to do, right? Now, what I'm going to do, I'm going to run this. And that builds a model. And it stored my model in a variable model. Now I'm going to click on the model. Okay, so what it did is that it outputs the call. Call basically is the command that I ran to build the model. And here are my coefficients and an intercept. And I'm going to explain to you what that means. Right? Basically, the method assigns the coefficient for each continuous numeric variable. It assigns a coefficient, right? And for each categorical variable, it's going to take a value and it's going to assign the coefficient for that value. So what it's going to take is that it's going to take the most dominant values and it's going to turn them into a set of the dummy variable, right? So what is it going to do? Basically, let me go ahead and run the summary command. It's going to make more sense, okay? So here, my summary command is going to show me the formula is a command that I ran to build the model. Here, the residuals, right? So residuals is basically the difference between the actual value and the predicted values. So here I have my intercept, right? So intercept basically is the area that is burned by the fire if everything else in here is if all other variables are 0. So if all of my other variables, if all of my other coefficients here are 0, this is what's going to be the area is like, right? So here, notice that what it did is this is a month is a categorical variable, and what it did here, it created a separate variable for each month's value, right? So I have August, I have a December, February, January, July, June, March, May, November, October, September, right? And you notice it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? Why 11? Because it picked 11 out of 12 months, which are the most dominant, right? It picked the most dominant. So basically, what it's doing in here is that when my month is August, we are adding 50.95 to my area affected by the fire, right? So the dependent variable is the area that gets affected by the fire, and it has a set of the independent variables. And now let me look at the, see here, this is a temperature, and this is a coefficient. So it means that for each degree in the temperature increase, if I increase the temperature by 1 degree, this is an increase in the area, right, that gets burned by the fire. So this is what basically it means. If I keep all my other variables constant, this is an increase in the area affected by the fire. Now, I want you to pay attention here. This identifies which variables are significant. And here, it shows you the significant codes, right? In this case, we don't have the 3, but we have 1. So basically, it's trying to say that this variable has a significant impact on the area affected by the fire. So here it is. and here it is, here, right here, days. And apparently, for some reason, it's saying that Saturday. Okay. So basically, again, what it's doing is that for this variable here, if I increase it by 1, this is a decrease, right? Because this is a slope, in other words. Now what you could also do is, so summary command gives you the residuals, it gives you the p-values, the standard errors, the coefficient, and an intercept, right? Now what I'm going to do here is that I'm going to show you what else you can do. You can show the cube distances, right? Or you can show the residuals, or you can also build the ANOVA table. That's a table that I was just looking at, the coefficients. Oops. Something went wrong. Oh, because I should not be highlighting. Here we go. So this is the ANOVA table that I was just looking at. Now what we're going to do here is that we are going to evaluate the module. We are going to evaluate the model on the test set, right? So the command is a predict, and I'm going to store the predictions in my variable. Run, right? Okay, so this is the predicted values. And now what I'm going to do is I'm going to make a plot of the predicted values versus the actual values, right? And the up line is going to end the line to the plot. And my goal is to make sure that my points are closer to the line, as close as possible, right? Because the line basically goes, for all points in the line, the predicted value is equal to the actual value, right? That's what basically it is. The predicted value is equal to the actual values. So now what I'm going to do is, basically what I could do is, I can just separately plot the residuals, right? So this is going to do just a separate plot of the residuals. Or I can just run the plot command, plot model, and I can just click enter. So I can show my plots one at a time, right? Okay, well, it gave me a warning, but you can ignore the warning. Now what we're going to do is we're going to build a minimum adequate model. So if you noticed over there before, if I do the summary command here, run. If I do the summary command, notice here it involves all of my independent variables, right? But some of these variables may not have a significant impact on a dependent variable. So what I'm going to do right now is I'm going to run this right here, plot. Okay, let me go back. I'm going to do the step function here. I'm going to build the second model, and I'm going to run the step function. There we go. And I'm going to store it in a variable. I'm going to store the final result in a variable called model2. So what this function is doing is that it's starting from all variables, and it's going to pick the variable with the highest AIC value, and it's going to remove it, right? It's going to remove this variable for right now. So let me see what's left. So this is a new one, right? And it's going to check if AIC has changed. If there is a change on AIC between the last iteration. It looks like there is, right? Yes, there is. So what it's going to do is it's going to remove my next variable right here. It's going to remove it, and then we continue. We keep comparing the highest AIC in here again, right? And we're going to remove it. Now again, we're going to compare it, and since there is a change, right? Still there is a difference, we're going to remove, and we keep on going. And notice here the last two iterations, The last two iterations, see there is no difference in here, right? So we keep. So basically, these three variables are the most significant, and this is our model. We can print this here, summary. Okay. And now I'm going to run this. This is a ANOVA function, and what it's going to do is here, first input parameter is a short model, short version, and here is a new version, right? And what this is, it's showing me the difference, right? And I'm going to go compare this number. Where does this fall? Since it does not fall anywhere between 0 and 0.001, it does not fall anywhere in this range, right? It does not fall anywhere in here. It means that our variables that we removed were not significant, right? That's what it does. It looks at the difference if it's significant, right? So this is your linear regression model. When do we use it? We use it when dependent variable is a number, right? You want to make sure dependent variable is numeric, and we're going to do a prediction, okay? We're going to do a prediction. That's when you use this. Now, we're going to switch gears here. Our dependent variable is not going to be numeric anymore. Well, it's not going to be continuous number anymore, right? Our dependent variable is going to be the categorical. And to do that, I'm going to look at the different data set, and I'm going to be looking at the, well, here it is, hard data set, right? The hard. And I'm going to predict if an individual has a likelihood of the heart attack. Since I'm going to have only two values, yes or no, right? Okay, since I'm going to have only two variables, right? I'm going to have only two values of the dependent variable. So let me do this. Let me do this now. Tools, import data set from local file, and I'm going to do this. I'm going to go back to my data sets folder. And what I'm going to do is I'm going to select heart. Here it is. Here it is. Right? So what I'm going to do now, look at this. This is my dependent variable, and it can have two values, as present or absent, right? So present stands for an individual has a risk of heart attack, and absent individual does not have. And I'm going to go ahead and load this. Now what I need to do is I need to record this class variable as 0 and 1. I want to record my present as 1 and absent as 0. Okay? Let me close this out. This is how I need to record this. First, I'm going to do is I'm going to convert this last variable to a character. Right? Let me run this again. And I'm going to convert this to a character. If you see this right here, oops, art. See this is a character right now. And now what I need to do is, here I'm saying if it's equal, if it's absent, I'm going to change it to a 0. And if it's present, I'm going to change it to a 1. So I have these two lines here. Now what I need to do is, I'm going to convert it to a number. I'm going to convert it to, because I need it to be a number, right? I cannot work with this as a character. So I'm going to do it as numeric. Now what I'm going to need to do is, I'm going to need to, again, divide my data into a training set and test set. But another thing is that I want my result to be reproducible. So what I'll do is I'm going to set seed, right? I'm going to set my seed. And what I'm going to do now is I'm going to divide my data into a training and test set. So I'm going to do this, right? I'm going to do this, train and test, right? So I divided my data into two parts. I picked 70% is going to be training and 30% is going to be test, right? The function to build logistic regression model is GLM. Instead of LM, we have a GLM right now. The syntax is the same. So here I have a formula. This piece right here, class, is the name of my dependent variable, tilde, and here I can list all my independent variables, or what I can also do is I can put the wildcard dot. It's a wildcard, which means that all my variables want to be used, right? Train data, it means that I'm using my training data to train the model, right? That's a data. And here the family is Gaussian. There are different types of models. I picked this. Let me go ahead and run this. Right? And I stored it in a variable model. And now I have to print this. Okay. Now what I want to show you, this is very similar. Output of this is very similar to linear regression. I have my formula. Formula is what I entered to run my model, right? And what I could do is I could, of course, create a variable formula the way it is in your Word document, right? And set it equal to this, and then just put in the word formula. I could do it, but the reason I didn't do it is because I want this piece to show when I run the summary. Now take a look at this. I have two dots, right? I have a 1 star, 3 stars. It shows the significance. So that indicates that probably slope and this number of major vessels and these variables are probably significant predictors of likelihood that an individual may have a heart attack, right? So this is not, this coefficient is going to be the odds ratio, log of odds, right? So if an individual is older, this is a change in the log of odds an individual has a heart attack. If I increase the age by 1, basically. And this is what happens if blood pressure goes up by 1, right? And here, the blood sugar, this is what happens if it drops by 1. And here, this is what happens when exercise induces angina. So this is what happens when the value is 1, right? Two values, 0 and 1. And here it shows that these two variables are significant, right? These 3 dots. Now what I can do is I can only display the coefficients. I'm just showing different options here, right? And there is a model fitted values. Fitted values basically are the predicted values. So what I could do in here is that I can do model. I can type this dot fitted values. Right? So my fitted values are the predicted values. So these values are the predicted for each instance, right? What I have to do is, in order to evaluate the accuracy of this model, I'm going to build the confusion matrix. This is called the confusion matrix. So let me run this. So basically, what I want to know is that I want to know how many instances, right? How many people in the training set were classified as do not have a heart attack, actually do not have a heart attack. How many people were classified as have heart attack, actually have heart attack, or how many people is classified as no heart attack actually have it, right? Or how many people that were classified as have it actually don't have it. So this is what it is. The table is a confusion matrix, and we need to look at the entries on the diagonal. The entries on the diagonal are the correctly classified predictions, right? Those are correctly classified predictions, and here are misclassifications, right? So in order to calculate the accuracy of a model, I need to take the sum of numbers on the diagonal and divide by the sum of all numbers in the matrix. Or this is one way to do it in here. Right? We're taking a mean of values where the value here, the value predicted equals the actual. So this is the actual value. I'm taking the value of the class variable from the training data, right? So here's an actual value. So here I can just basically do this. I can calculate. And this showing me that the accuracy of a model on the training set is 85%. And I can also calculate misclassified, right? So I'm going to have not equal here. Now what I can do is I have to use my test data to predict the model. So notice that if I take this, like this right here, it's going to give me the predicted values for the test data. For some reason it is negative, but it doesn't matter, we're going to round it. So basically, this is odds ratios, right? Predicted. And what I'm going to do is, I'm going to now build the table, and what I want to see is how many people were classified as have heart attack actually have it, and how many were classified as not actually don't. So here it is, right? This is on the test data, and in order to do the classification accuracy, I have to add the numbers in the diagonal, right? And I'm going to divide by the total. So something else to keep in mind in here, if an individual who does not have a heart attack was classified as has a heart attack, this is called true positive, right? And if it's another way around, false positive rather, false positive. If an individual was classified as has heart attack but actually does not, this is going to be the false positive. So we have true positive where an individual was classified as has heart attack, actually has it, and we have a false positive. If we have a true negative rather, right? When an individual was classified as does not have a heart attack, actually does not, right? So now what we have to do is we need to do this, and we have to calculate this, right? So this, here what I just did, this is a classification error, and this is accuracy, classification accuracy. So, oops, what I did, I have to do this. I'm sorry, my mistake. Copy. I have to take this, and I have to change it to the equal, like this. My mistake. And I'm gonna do this. Run. So this is the accuracy. For some reason here I'm getting it on a test set higher than training set. It's possible, but usually you get lower. What I could do here, I could also do the step function. I can run the minimal adequate model. So what it does is, it takes the one with the highest AUC, basically what it did is it just, in this case it's removing the one with the lowest, looks like, yes. So it basically, and it stops here when there is no change in AIC, I'm sorry, right? Because if you look at it here, we were doing something similar, right? Something similar. Look back here. Yeah. So basically here, back here we were running this too, right? See this? I'm sorry, my mistake. It's removing the one with the lowest AIC. We are removing the one with the lowest. That's my mistake, right? So on each iteration, we are removing the one with the lowest, not highest, lowest. And basically, what's going to happen here is that the method is going to stop when AIC no longer changes. When AIC no longer changes, we're going to stop right here. So basically, the remaining variables here happen to be the most significant. And what I'm going to do now is I can test it by actually running this ANOVA. And I'm going to compare this number against the significance numbers in the ANOVA table, right? And if you do compare this, you're going to see that this number does not fall within any of the intervals, right? So let me go back here. Let me run the summary command right here. Right? I'm going to do that. See this? We look at these numbers, right? Since it does not fall in between any of these intervals, we can tell that the components removed are not insignificant, right? So now what we're going to do is, this is a bonus part, we're going to draw the ROC curve. And the ROC curve basically tells us how good is our model. We want the area under this curve to be above, we want it to be closer to 1 rather, right? To do this, you have to install the variable, you have to install the library. And the library is called ROCCR. First, you have to install it. But since I have it installed already, I have this package installed already, I have to load it into memory. Right? I got it loaded into memory. This is not the error message. It's just telling me that the package was loaded. Now what I'm going to do is, I'm going to store my predictors. I'm going to store my predictors in a variable called predict, and I'm using the test data, and type is a response. So I'm here, I'm going to store my, I'm going to store over here my predicted values. Run. Oh, sorry, my mistake. Run. Now what I'm going to do is, I'm going to run the prediction command, and I'm going to store the quality of my prediction into this variable. So prediction is going to take the predicted values, and here, this is telling me that this variable, this is the actual value, right? So here I'm passing the predicted and actual value, right? So what I'm going to do, I'm going to just run it, right? And let's see what it is actually. Let's see what it's equal to. So see this? This is what it did, but what we're going to need is, we're going to take from this, we're going to take the true positive and the false positive, right? That's what we're going to do. We're going to take these two components, and we're going to plot them. We're going to build this plot. So let's do this. Let's plot this. Oops. Sorry, my fault. That's my fault again. What I have to do, I have to hit escape. Okay, let's do this. Oh, this is my fault, guys. Okay. Okay, there we go. Now, let's see if it's gonna work now. It should. Oh, because I never ran this. Sorry. Run. Run. Okay, there we go. Now I have this, right? So basically what I did was, I did true positive rate versus false positive rate. Now, remember this. True positive is basically when I predicted that individual as an individual has a heart attack, and that individual actually has a heart attack. And false positive is when I predicted that my individual has a heart attack, but individual does not, or as a likelihood, right? So that's what it is. And we want to make sure that this graph, that chart is here, is closer to 1 or away from the diagonal. So just to make it clear, I'm just going to draw this diagonal line in here. Right, so this is the diagonal line, and I want to make sure that my graph is above. Right, it shows how good my model is. Now what I can do is I can plot my predictions. Right, I can do the residuals plot. So what I'm going to do here is that I'm going to take the residuals. Right, remember this? I can compute the residuals, and residual is the difference between the actual values and predicted values. Right? So we have an actual likelihood that individual has a heart attack, and we have a predicted likelihood. And what I'm going to do is I'm just going to plot it right now. I'm going to produce the residual plots. That's how it's going to look like, 2 lines. And now what I'm going to do is I'm just going to draw the actual graph here, right? There we go, right? So this is how you do this. But if you do the plot command, right, you're gonna get all 4. See this? If I do plot model, I can do this way too. But I just show you the alternative way to do this. If I do plot model, I have to do this. See? This visualization is something similar to what I had. Residuals versus fitted, right? I had something similar. But I just showed you another way to do it, right? So this is your logistic regression model. Logistic regression model predicts the likelihood, right? This is a likelihood that an individual will have a heart attack. So we are not predicting the specific number, and this is a classification because I'm building my confusion matrix. Okay, so next one I'm going to go over is a naive Bayes. Here, what you need to do is you have to install this package. You need to install E1071. This is the package name, right? And when you log in, on your next login, right, when you start the new session, and when you need to run naive Bayes method, you need to load this package into the memory. Now what we're going to do is we're going to do some data pre-processing. Oops, I should load this data again. I'm using the same data set. So let me load this again. And the data pre-processing is going to be the same. But let me explain it to you again. So what I did was I converted the class variable to the character. And now I'm going to do set absent to 0, at present to 1. And I'm going to do this. I'm going to set this as factor. And now what I'm going to do is I'm going to set the seed value. And the reason is because I want my result to be reproducible, right? Run. And here I'm going to divide again my data into a training and test set. And now I'm going to run my model, exactly the same approach, but I'm going to do, it's a different function. And this is available in this package over there, right? But the idea is the same. It's going to take my formula as an input, and what I did was, oops, I'm sorry, here. The class variable is a dependent variable, and that means I want to use all my variables. Now, good news, this method, all of this, in this method you can use a wildcard. Right? In other 2 methods that we did tonight, linear regression and naive Bayes, you can. But in some methods you're going to see in the next module, you cannot. It would have to actually spell out all variable names. In this method you can. You don't need to spell out. If you want to use all of them, you can just put dot. Here is my training data, right? I run this. And now what I have to do is, well, I can do this. I can do summary model it's gonna give me two parts here. It's gonna give me two. I'm gonna show you what it does. Oops. So basically, here, what I did was basically I did not discretize. I did not discretize my numeric variables. There are two ways to handle this problem. I can discretize all my numeric variables. Then the method would be looking at the probabilities, right? The method will be looking at the probability of each value, basically, right? But since I did not discretize it, right? What I'll have to do is I have to look at the different pieces of the model. First, I'm going to look at this at a priori. And basically what this is, it's telling me that based on my training data, there is, in my training data, 110 out of 86 instances have no, and here is a number of instances that have yes, that individual has a heart attack, right? So now what I'm going to do, this is the tables, and the tables basically is going to show me for the numeric variables, it's like age, it's going to display the mean and the standard deviation by each value of the dependent variable. So it's going to look at the dependent variable 0, right? It's equals 0, and this is the mean and the standard deviation. This is what it's going to do, basically. This is how it's going to behave for the numeric variables. And this is a categorical variable. For the categorical variable, it's going to give me the probabilities. Suppose that an individual does not have a heart attack, right? Given that an individual does not have a heart attack, what is the probability that my individual is a male, right? This is the probability that an individual is a male, given that an individual does not have a heart attack. Here is a probability that individual is a male, given that individual has a heart attack, something like that, right? So here it's going to be looking at the conditional probability and an overall probability of a class, right? So to get the probability of a class, I would have to take the sum of these two numbers, right? It's going to be, for instance, this number divided by the sum. It's going to be the probability that individual does not have a heart attack, right? So basically, this method is using the prior probability. And because if you notice that if you compare it right here, this is the age, right? If you notice that if I do this, if I compute the mean for the age by a class, and if I compare, the numbers are almost equal. These numbers, if I scroll up, they're almost equal, right? So basically what I'm saying is that for numeric variables, it's going to be taking the mean and standard deviation. For the nominal variables, it will be looking at the probability of a class. And what I'm going to do now is I can do the confusion matrix, right? It's similar to what I was doing before. So this is a confusion matrix. Basically, I want to see how many people do not have a heart attack were actually classified as do not have a heart attack, and how many people have a heart attack were actually classified as have a heart attack. And I can do the accuracy, right? I can do this, right? And now I can evaluate my model on test data. So this basically is showing the predicted. Predicted is going to be either 0 or 1, right? And here I can just do this is a classification, accuracy is 87%, and this is a misclassification, right? So basically that's what it is. For For the prediction, for the classification, you look at the confusion matrix. And for the prediction, we looked at the residuals, right? We looked at the differences between predicted and the actual values. So I just went over 3 methods, right? So you have the linear regression, logistic regression, and naive Bayes, right? And now is a good time for you guys to ask me questions. I love questions. So let me go ahead and let me open the chat. Please go ahead and ask me questions. I love questions. I love excellent questions. And if some of you may have had me in other coursework before, you know that I love when people ask questions. And if people don't ask questions, then I ask questions. Okay? When people don't ask me questions, I start asking questions. So, in a forest fires example, why do you think I did not use naive Bayes method? Why this method is not a good idea for the forest fires, right? And the reason is because my dependent variable area is numeric. I want to predict the number, specific number. I don't want to predict a class, right? I don't want to categorize anything. The area is a number. This is what I was doing here, right? So something to keep in mind, and this is also going to be your homework assignment, where you're going to use a different data set, but you will be predicting, I believe it's a car price. Yes, so it's a number. And if you notice that here I did not remove any variables, but in the homework assignment I ask you to, because if you look at this, right, if you look at this till import local file, data set, data, oops, this one, and I'm gonna show you why. Okay, here it is. This is your homework data set, right? And I wanted to show you something. So if I do this, if I do summary, if I run the summary command, oops, I need to learn how to spell sometimes. Okay, so now what I want you to see is, I want you to look at the categorical variable, and I want you to notice that, this is a different data set. I think I may have asked you to use import, my fault. But in any case, I ask you to use the imports, right? Oops. So let me go back to my data answer, okay. And I ask you to use the dataset name is import, right? Here it is. And I'm just gonna call import, and I wanted to show you the reason. Okay, import, and I'm just gonna do this summary, and I'm gonna put imports. Okay, take a look. Take a look at this. See what's happening? I have, for instance, number of cylinders. Do you see this? Do you see the problem? I have only one instance with this value, right? I have only one instance in this value. But we need to keep in mind that the method is going to create the dummy variable for each value, for each dominant value of the categorical variables, right? For each dominant. So see this? I have 12 and 3 with just one value. If I have only one value, what's going to happen when I divide the data into the test set and training set? Apparently, I'm going to have an observation in the training set with a value that's not in the test set, and I'm going to get an error. So this is the reason I asked you just to go ahead and remove those variables. And I just did it to help you because honestly, in the past semesters, the exercise did not have that hint. And what was happening is that it was very difficult for some students to resolve the error message. So yes. Okay, excellent question. So now let's see. In regression analysis, we usually check to see if residuals are normally distributed. Do we need to do this? Yes, you do. Yes, you do. Not for naive Bayes, but you need to do this for the linear regression and for the logistic regression. Excellent questions. Yes, you do. Yes, you do. Okay. Basically, yes, you need to do this, but not for naive Bayes. Oh yes, excellent, excellent. I'm gonna explain to you the. Can you explain the confusion matrix, the diagonal? Okay, I'm gonna go ahead and explain it to you right now. So let's go back to the confusion matrix, and I would need to go scroll up. So basically, here, right, I have a predicted values, and I have an actual values, right? Here, basically, what I'm saying is that my predicted value is 0 and actual value is 0, right? So I believe column, this is a row, right? And this is a column, I believe. Or the other way around, I have to check. But if you look at this, right? I never remember which way it is, but if you look at it here it is. See this? Here it marked for you predict, right? The confusion matrix here, it's showing you here that each matrix, the row label is a predicted class. Okay, the row label is going to be predicted, and a column is going to be the actual, right? So here, basically what's happening is that the row label is a predicted, and this is the actual. And the intersection right here is going to tell me that I predicted that 99 people don't have a heart attack. And in fact, 99 people don't have a heart attack. Here, I predicted that 67 people, right, have a heart attack, and 67 people actually have a heart attack, right? So, the diagonal entries, on each diagonal entries, right, I have the actual value matching the predicted value, right? Here. This is a count. This entry here tells me how many instances I have predicted as 0, that actually 0. Here, predicted 1, but actually 0, right? So this is misclassified because I predicted it as 1, but it's 0. And this is also misclassified because I predicted it 0 and this is 1, right? So how do I know percentage of instances that were correctly classified? These two numbers in diagonal, right? Because the predicted class equals actual class. So I have to take the sum, and I need to divide it by the total, because total is the total number of instances. So this is going to give me percentage of correctly classified. And usually what I do is I look at this. See this? So here is your training set. And in the training set, I have 900. Oh, this is a test data, rather. I'm going to go back to my test data in here. Test. And I'm going to check how many observations I have. Right? And actually, let's scroll back up. Train. Sorry, this is a training, right? So what I'll do is I'm going to look at this training data. I have 196 observation, right? So out of 196, what I have to do is I have to add, I go 99 plus 67, right? Equals, and I divide it by 196. Divided by 196. this gives me the classification accuracy. So this is one way to do it. I did it on a calculator. But here what I did was I'm taking the mean of the, I'm looking at the predicted, right? And I'm checking if the predicted is equal to the actual. And if predicted is equal to the actual, it's a 1. If not, it's a 0. And I'm taking the mean. So that's how it's going to give me the accuracy. And here it's the other way around, not equal. So basically, this is one way to, this is how you would calculate it in R. But also for your paper, you can go ahead and do the, you want to use a calculator, you can do it too. So because predicted was put first, exactly. Predicted, it went to the row, that's right. And actual went to this here, yes. Excellent, yes. This is a confusion matrix, yes. So basically, this is only for the classification. Keep in mind, this is only for the classification, right? And you will see this again. In the next module, you will see this again. Except here, you only have two classes, two values, 1 or 0. Later on, you're going to have more than one class values. You're going to have more than one class values, trust me. But we're going to get to it. But first, we're going to do this logistic regression and the naive Bayes classification method. Yes, and something that I wanted to point out is that naive Bayes method assumes that all predictors are independent, right? It's going to assume that all variables equally contribute toward the end result, so to speak. Right? For linear regression exercise, if the model shows that there is no linear relationship, can you still run the model? Absolutely, yes. You still run model as a test set, yes. And what I wanted to point out that, in fact, we need to keep in mind that the relationships are not always a straight line. So if I give you the set of the independent variables, right, and the dependent variable, we cannot always draw the straight line. Well, let me explain it to you better. Suppose that you have a plane, and the plane has a set of points, and we want to draw the line through all of the points, right? Can we always draw the line? No, the points not always lie on the line. It could be hyperbola, or it could be the polynomial, or it could be another equation, right? It's not always a line. So similar, when we have multiple dependent variables, we have it's called hyperplane, right? It's a hyperplane. So sort of like a line in multiple dimensions. And not all relationships are linear, absolutely, right? So you just explain it in your paper. This is an excellent question. I like this question. And if you might be interested, you could actually read on polynomial regression. Well, I know it's not required for this class, but it's something that you might consider in your leisure. If you have a free time, you might be interested to read in a nonlinear regression where the assumption linearity is dropped, right? So in your exercise, keep in mind that linear regression, it assumes the presence of linear relationships. There might not be, but it's a task to prove that there is not, right? So basically, we are not evaluated on the result, but we are rather evaluated on the interpretation of the result, right? So yes, you still evaluated on the test data, and you have a solid explanation. But this example that I picked for this demo, it's actually for the linear regression problem. The relationship is linear in this specific example. But I'm not sure if you may or may not remember back in was it the pre-calculus class where you had a set of points and you tried to fit the model, where you would try the different types of model and determine which model fits better? right? So same thing here. Method may or may not work well on a certain data set, and sometimes you may want to evaluate two models and compare the results and to determine which model is the best predictor. And if you may have noticed, for some reason, when I ran the naive Bayes here, I got a higher, slightly higher classification accuracy than with logistic regression, right? So, yeah, but that was an excellent question. I like questions like this. Excellent. So let's see who else have questions. I like questions. So I was not sure if after looking at the residuals plot seeing no linear relationship we need to go. Oh, well, you don't need to go with it for this exercise. You don't need to do it for this specific assignment. But if you were doing the research study, a research project, then you would, right? If you were taking the there is another variant of the data mining course in a database program where they have a big project instead of small assignments. The way you have a biweekly small assignment, they have a big paper, and they need to use at least 2 or 3 data mining methods and to compare the results. I mean, there is another variant of data mining course in the database program. That's where they need to run at least 2 or 3 methods and compare the results. So, but for this specific exercise, no, you don't. But it's a good, yeah, sure. You're the most welcome, yeah. But it's something for you if you want to learn more. It's something that you might want to try on your leisure. And it's something just to help you get more familiar with the concept and study this topic some more in depth. Because, I mean, honestly, we could have the whole book on the classification. So it's very deep topic. It's a lot of concepts. And so basically, for this specific exercise, you just run linear regression and interpret your results and just make sure that the assignment submissions shows application of concept. That's important, right? And this piece here, it was a bonus. So basically, I like to show something a little bit that's not in a exercise document for people who watch the WebEx and for people who attend the WebEx. I want to do something like a little bonus. So tonight's bonus was plotting the RAC curve, and I also showed you how to do this the calculation if you don't have a calculator near you or something like that. Well, we always have a calculator on the laptop, but in just another way to do it, right? So let's see what other questions we have, because I like questions. Right? So yeah, go ahead. Please ask me questions. So basically, questions, questions. I love questions. Okay, is there? Yes. So basically, this is a difference. You take the difference between the actual values. Excellent. That's excellent. You take a difference between actual values and the predicted values. Because basically, if you look at it, it's a square because it's a distance. Uh, remember that Plato was there? We had that, oops, we had that plot over there. You're basically looking at this distance. You're looking at the distance to that line. I have to find this. Yeah, so see here, you're looking at the square distances. Yeah, you look at the distance, how far this point is. Well, of course, there's always going to be the error, right? There's always going to be the squared error. And it's taking the sum. Yeah. Sarah, what do you mean the dollar of price? I'm trying to understand the question. I'm trying to understand what the question is. I'm sorry. Because basically, what it is, yes, it is a, well, I need to look at the output. RSE, does it mean? Oh, yes, that's right. That's right. Excellent. Yes. Yes, so it tells you how far off it is. Right. Right, but you would have to take a square root because it's a squared, right? You would have to take a square root. Yes. I'm so sorry. I was not sure what you meant because you, yes, because you were looking at the vehicle data set. I'm so sorry. I'm sorry for misunderstanding because you were looking at the vehicle data set while I was looking at the area. I was looking at the forest fires area prediction. So that's why that was causing the confusion. But I understand the question right now. Okay. But I'm so glad that you asked. Yes. This is interesting, and I love these questions. Yes. So, but for this week exercise, you're doing the linear regression, and the next week you have a choice: logistic or naive Bayes for the next assignment. What was the question? Oh, Sarah basically asked the question how the RSE translates. The RSE is the square difference between the predicted and actual values. So basically, Sarah was looking at the car price, and she was saying that RSE is $2,984, and she was wondering if this is on average, is it how far off the price is. This is what basically it is. So she was just asking what that number means for the price data. That's what she was asking. Yes. Sure. So, yeah. And I'll just give you a little hint. You want to replace the missing values with the mean, okay? And the reason is because the step function does not work with missing values, right? Step function does not work with missing values. Oh, in fact, I forgot to tell you something. For the naive Bayes, there is an option. There is an option here. If you type this, let me show you something. If you type this method name and a question mark, it's gonna show you the option. Did we need to do anything with outliers? Just NAs. You just handle NAs. Yes, Carl, you need to handle the missing values. You need to replace them with you replace the missing values with the mean. Yes, you do, because otherwise the step is not gonna work. Yes, the mean. You replace it with the variable mean, yes. But for the naive Bayes method, right, that you're gonna use, let me show you something. There is an option on missing values, and Caesar, do you remember this NARM? Caesar's NA option. So when you run naive Bayes method, you can specify how to handle the missing values. You may specify it to ignore. See this? So this is the default action is not to count them in computation. So this is how naive Bayes will behave. By default, it's gonna ignore the instances that have a missing values. So that's for naive Bayes. Can't you drop few missing values? Well, yes you can, Sarah, yes you can, but the problem is you're losing the observation. This data set is small, you're losing observation, and you may need to remove some additional variables. Because when you lose variables, you may introduce more categorical variables with only few values. Because when you look at the categorical variables, there is a risk that whenever a data set is small, there is always a risk that you're losing data. So, but either way you did it in the homework, either way would work, as long as you explain it. But if you notice that you're getting NA, right? If you look at your output here, the ANOVA table, if it shows NA for the coefficients, then it's going to indicate a problem. You would need to remove this variable. If you're getting NA, right, then you're going to see what I mean. It's going to be a problem. You would need to go ahead and remove. Yeah. So basically, the reason there is a hint to remove four variables is because of what I showed you here. Right? And before I did not put this, and yeah, it was my mistake. I should have said right away to remove, right? Or I could change it. Next semester I could change it. I could say, let's code this in a category called others. We can do this, right? Because we don't want to lose data. We can say if number of cylinders is 8, 3, 12, and 2, we can create another group and call it others. Same thing here, right? We can just group it. That's another way to solve this. And that might be even more efficient way, but either way, if you do it by grouping, that's a big plus, but removing is fine. For this specific exercise, removing is fine, right? So, and yes, let me know what questions you have. This is a good time to ask questions. And I'm sure that you will have more questions on logistic regression and naive-based method as we go through the next week, right? Next week, because you're going to be doing the regions, yes. It will also happen that if all names are removed, some categorical variables will lose levels. Excellent. Yes. Yes, exactly. You're losing levels if you remove the NAs. And not only losing levels, there is also risk of having only one instance in each level. But then, if I'm dividing my data into two parts, right, what's going to happen? I'm going to have a variable, I'm going to have something in the training set which is not in the test set, and this is a big problem. I don't want this to happen, do I? No, because I'm going to be getting an error, and the error message will be caused by having more. It's going to say that the number of variables is not the same, right? It's going to show me that the number of variables in my test set does not match the number of variables in the training set. It's because it's looking at the categorical variables and it's going to treat each value as a separate variable. It's creating the dummy variables for you, and I think we need to appreciate that the method does it automatically for us. Some methods do not. Just giving you heads up, some methods like neural network methods, they do not. There will be an extra step that you would need to do to convert the categorical variables into dummy variables. But this will be covered in the next module. All right, but it just a quick preview, just to give you a little bit discussion of something that we need to appreciate while we have it. All right. So just keep in mind that logistic regression and linear regression method create dummy variables for us. We don't need to run anything extra for that, right? And also make sure that you understand what intercepts mean and what coefficients mean, right? So what else? I'm trying to think. What else I have not covered? And you understand also why we said seed, right? Because I want my results to be reproducible, right? So, any other questions? questions? Going once? Okay. Oh, exactly, yes. Yes, yes, yes. Excellent, Sarah, yes. You set the seed if you want to run another model, yes. And another thing is that, suppose that, sure. Suppose that what I do right now is that I start this exercise, and then I say what I did, and suddenly I turn off my laptop. But I already did it. I'm halfway through my homework, and somehow I turn my laptop off. When I turn my laptop back on, I want to be able to reproduce the work that I had, right? That's why. So my results are reproducible. If I have to come back to my assignment. I don't need to redo in my write-up what I already did. I can just continue. I can rerun the commands that I ran and pick it up from there, right? Okay. The intercept will not always have a logical meaning, right? Well, yeah. So basically, an intercept is, in this case, is going to be the area if all the independent variables are zero, right? So it's something similar to when you have a line and it's an intersection. It's a point where the line crosses the y-axis, right? So this is something similar here. This is something similar. You use randoms that they create the new random set. Well, yeah, I use that random to divide. I use this to divide the data into the training and test set, right? It's randomly. I'm kind of like randomly selecting 70% goes to the train data and 30% to the test data. I mean, you can go ahead if you like and try to play with different numbers, but this is a recommendation from the R textbooks. So I just follow it. But yes, for the intercept, basically, yeah, it's a, in this case, well, in this case, you have a hyperplane. This is not a line, but it's something similar. Because when you have a line, regular line, you have a y-intercept, right? And you have a slope, right? So it's like y equals to whatever intercept is plus x times the slope. We have something similar here, except we have more than one independent variable, right? We have more than one independent variable in this case. So this is called a hyperplane, right? So, and what you basically do is, yeah, you need to create the minimum adequate model. So basically, you're trying to keep only relevant variables, right? And you want to eliminate the ones that are least relevant. Yeah. But I have excellent questions today. Excellent. So, yeah. Another something very important that I may have forgotten to point out is that, so basically when you have your linear regression model, right? It's a model, basically. This is actually a model. If you look at this, you have the coefficients, right? Oops. So basically your model is going to be this. It's going to be this intercept plus the product of whatever the independent variable is. See, for the independent variables, it's going to take this, right? Whatever this value multiplied by this right here. If day is Saturday, it's going to add this to the area. If day is Sunday, it's going to add this number to the area, right? That's how it's going to do. So now, suppose that I have a totally new instance. I have the values of all independent variables. How do I use this model to predict the area affected by the fire? Basically, very simple. I just take my variables of independent variables and plug them in. That's it. I just plug them in. I'm just going to look, okay, what is my month, right? And suppose it is May, right? So it's going to be this minus this, right? I'm just plugging it in. And then I'm going to look at what my day is, right? If it's Sunday, I'm just going to add this much. Then I'm going to look at the value of this variable, oops, right here, and that's going to be multiplied by this coefficient, and so on, right? What I do, I just plug it in, that's all, right? So this is how you do it here. Yeah? So let's see what other questions we have. Because this is a good opportunity for you to type questions in the chat, and I really enjoy doing WebEx, and I enjoy questions. So to plug it in categorical, well, not okay. Excellent questions. For the categorical variables, you're just gonna use the coefficient depending on the value. We are not multiplying anything. We're just selecting. So basically, if the month is August, right? We use this number. If the month in December, this is the number that we use. The number that we use here is based on the value. That's all we do. But if it's neither, then nothing. If it's neither of this, then it's nothing. Zero, right? Yes, excellent. You use the correct coefficient. Excellent, sir. Sir, excellent observation. You just take the correct value. Right, exactly. And if it's neither of this, then it's a zero, right? Because what it does is, I know we have 12 months, but it took 11, the most dominant out of 12, and listed them here. It picked 11. And the same thing for the days, right? Because I know we have 7 days in a week, but it took the six the most dominant in here. And it omitted the least dominant. Well, of course, because if it's neither of these 6, right, then we know it's the least dominant day, right? So, and this tells you the significance level, right? Yes. And let me see what else we have. For the numeric variables, yes, for the numeric variables, well, yes, you're going to use the coefficient. For the numeric, you're going to use the coefficient next to the number, right? Like, for example, temperature. Temperature is a numeric. So basically what it means is that if I keep all my other variables constant, if I increase the temperature by 1 degree, this is an increase in the area affected by the fire. This is what it means here, yes. So you take the temperature and multiply by this number, yes. So this is an increase in the area if the temperature is raised by 1 degree, assuming that other variables remain constant. It's a slope, right? So slope is a change in the dependent variables when the value of independent variables changes by 1. Right? That's what it is basically. And each variable here has a slope, and we have a y-intercept, right? Well, we cannot really call it a y because we have a hyperplane, but you got the idea. So if the temp is 78 degrees, well, basically it's not necessarily 78 times 1.54, but it's for each increase, right? Oh, yes, exactly. That's, I'm sorry, Sarah, I misunderstood the question. That's what it's going to be like, yes. 74 times 1.54, that's right. That's right. Right. So you plug in the temperature, yes. But if the temperature goes up to 79, then the area is going to be increased by 1.54. Right, exactly, you got it, yes. And RH is the relative humidity. So if I increase the relative humidity, then the area drops. And if I increase the wind speed, the area is going to go up. Of course, the rain is going to drop the area, right? So here we basically have the location. X and Y are the coordinate. It's about the data was collected about the Rainforest Park. It's about one of the parks, and X, Y are the location in that park, right? And after this meeting, we're gonna pause the recording, and we're gonna pause the we're gonna pause the R scripts. But first, this is what I'm gonna do. I'm gonna take the recording. I'm gonna try to remove. There are 2 minutes in there that are not, that I'm gonna try to remove, right? And I'm gonna pause. We're gonna pause the rest of the recording. But I would need to edit it a little bit on the first, after the first minute. So bear with me, but the recording will be posted for this video. Yeah, so let's see what other questions we have. So let me see, going once, going twice. Still waiting. Okay. If you don't have any more questions, we're gonna call it a night. I'm gonna stop sharing my screen. And I'm going to end the recording.